Hi guys, nice to be back and see you all here. Welcome to the second session of our drone workshop series. Yes, today we will work on several simulations about structural design. So this is here we will continue, let's say, developing our drone, improving it. And yes, before I start with the webinar and we really start to dive into this very interesting topic, I would just like to check if you all can hear me and the webinar is working fine for everyone. So please press the raise your hand button if you can hear me. Nice, I see a lot of hands. So therefore, I think everything should be fine. In the case you have any technical problems, just use the chat or the question function of GoToWebinar, and I will try my best to get this solved. In the case that you have some problems with the webinar, sometimes it can help to leave and re-enter the webinar. Yes, but therefore I think we are prepared, and then let's directly start with our second session. Yes, this is maybe for those of you who were not here the last session very important. Let's just talk again some seconds about this workshop. So the idea is that we want to show you how you can use engineering simulation to optimize your own drones if you're maybe involved in do-it-yourself drone design or some other radio-controlled devices. And yes, last session we investigated how to optimize the aerodynamic of a propeller with using fluid flow simulation. Today we will talk about structural design of drone parts, and in the next sessions we will talk about virtual crash testing and vibration optimization. And the agenda of today is quite similar to the last session, so there will be a kind of very short introduction about the, let's say, fundamentals of physics which we are investigating here. So what are the physical effects we want to investigate with simulation, and how is that related to the performance of the drone? Then we will together set up again a simulation, make some result interpretation, and later on I will present you the next homework assignment, and we will have some time for question and answers. Well, maybe just to introduce myself, yes, my name is Milad. I'm working here at SimScale as academic program manager, so I'm responsible for our academic program, which provides free access for universities and students and researchers to SimScale. And I'm also very much involved in everything which is related to how to learn the platform, and also cooperations with external partners from academia and research. I have a mechanical engineering background, so I've studied mechanical engineering in Germany. I was a major in combustion technology, energy technology, and biomedical engineering. And you can imagine that simulation plays there a big role. And yes, so I have some experience with several applications of simulation technology for a high bandwidth of different industries, and hopefully I can explain you to everything you need to know to get started with SimScale, since our aim here is really that you guys are able after this webinar to use simulation for your own product designs. Yes. Just to make it crisp, this workshop is really very hands-on, so we want to give you some first experience with simulation and give you some let's say insights how simulation is used in industry, especially for drone design. This is however not let's say a detailed professional training for simulation, so we will not cover anything related to simulation theory. If you're interested in really this background knowledge, which can be very helpful, especially then when you want to, let's say, create advanced simulations, there are a lot of good books which I can recommend you. And also, if you're visiting a university or student, there are a lot of interesting lectures about that. And this is for sure also not a detailed training which is showing all functionalities of SimScale. For this, we have, for example, a lot of learning resources online, and we're also offering professional training for which you can, by the way, qualify for free if you submit all homework assignments which we are presenting to you. And just because some people were asking, this professional training is really the same training we are selling to our customers. And in the end, it's not a competition. You just have to be, let's say, be active during this workshop. So just do the homework assignments, and then you will get this free training. And a lot of people also ask, why are we doing this? And for sure, we are a company, but in this case, we are really I should really mention that we are putting a lot of focus in teaching simulation. This is something which is very important for us, and therefore we really want just to help interested engineers to get access to SimScale, and for sure would really appreciate if you have some product feedback for us. May some of you want to simulate their own geometry, their own design. There was, for example, some guys who asked for the last workshop while doing the homework for more enhanced modeling technology for rotational devices. And if you have, for example, a nice simulation you want to share with us, we can also put it into our public simulation library. And for sure, what we also would really appreciate is if you guys would help other guys on the forum. I think it worked quite well the last days, especially thanks here to Yusuf, who was very active, or also a lot of other guys of you who helped. And yes, that's it. Maybe just let's talk about just some question which were asked several times in the forum or via email. I think everybody knows that the workshop is going to be recorded, and we will provide you with the recording tomorrow before lunch, let's say. You don't have to do anything right now, like start to do the simulation. Just enjoy the workshop, note your question, and later on, yes, in more than 1 week, you have time to do the simulation homework assignments. You all can simulate yourself. So together with the registration of for this workshop, you were provided with a 5 weeks free trial version of SimScale, so where you have full access to all functions. And if you're a student, by the way, and you have academic plan, you can for sure access SimScale every time you want for free. And a lot of people also asked for support, and yes, we're providing support. But I would really ask you, please use our forum, which you can find on forum.simscale.com. And there we have a special place, workshop and webinars, and there is subcategory drone workshop, which is just about our workshop. And as you can see, we are providing there also for every homework assignment the step-by-step tutorial. And if you have any questions, just post them under the related topic, and as you can see, you will get very quickly support, and by us, or if someone of you is faster, by some other guys attending this workshop. And the reason why we are asked to do this is that a lot of people have the same problems, and then it's for us and also for you quite faster and better if all the questions and answers are accessible for everybody. Yes, and yes, if you, for example, have some questions or would like to do some more advanced topics which are not covered here, just feel free to discuss in the forum. You can use our simulation project library, which I mentioned before, which is accessible on simscale.com/library. Oh, small typo. And here we have hundreds of ready-to-use simulation which documented and which you can use as a first inspiration, for example, to get familiar with some more advanced stuff. And also something which was asked several times, how can I submit my homework? Some of you guys were mentioning that it's hard, that there is no confirmation email. So if you've done your homework, you can use this form to submit it. You can find here. And I know we announced that the deadline is today at 4 p.m. Just because some of you were asking, we will extend only today or only for this workshop the deadline till tomorrow 9 a.m. So if you are not completely ready, you have still some more hours. And but this also includes that we will release the next homework, so the project links as well as the tutorials tomorrow at 9. I hope it's okay for everyone, and just put here your email address when you want submit something that you use for signing up for the workshop, and put here the public links of your project, and then you will also get a confirmation email. We just implemented it today in the morning. Great. Then before we start, I would like to say thank you from the whole SimScale team. Yes, it's really great to see how many of you are doing the homework, are interacting with us and other users in the forum, and it's really a lot of fun for us to have this workshop together with you. And yes, thank you very much. Before we start with the let's say more physical things and talk about simulation setup and stuff like that, are there any questions that you would like me to answer right now? In the case, please. Oh yes, there's the first question. Just 1 second. Um, I have to load. Okay, yes. David wants to know how it's about sharing projects which are running. That's a good question. It was also discussed in the forum some hours ago, I think. In the best case, please just share your project when all simulations are done. It's theoretically possible to share the project while the simulation is running, but if we then import the simulation to check it before your computation is done, we will not see it, because in the moment where we are clicking on this link, it's somehow synced with your stand of your project and in your workspace. Therefore, if you're sharing a project with us, maybe because time is not a lot of time till the deadline, and it's still running some of the calculations from the jobs, please send me parallel email that I know. But I would really ask you, please, guys, if it's possible, just send us a simulation which are completely computed. Well, then let's start. And yes, as I mentioned today, the workshop is about structural design of drones. And there are a lot of aspects when we talk about structural design. Today we will focus on something special about the joint or the connection between the arm of the rotor and the two ground plates. And before we start to talk about this, let's say, example, let's maybe talk about some general things about the role. And maybe it sounds stupid first of you, but it's really something to think about the role of a screw or of a bolt. Most of the time you're designing a product, it's a reason of economical reason, or it's a reason of manufacturing not possible to manufacture the whole product out of one part. And then you have to join different parts to assembly. And there it's very important how you to connect these parts. And in our case, we're using bolts to connect the arm of the drone with the chassis, with the base plates. And whenever you are connecting, let's say, two solid parts using, for example, a screw and a nut, then there are basically two options to connect these two bodies. The first option is, just imagine you would not have a. Just imagine you would just have these two parts here, and have this bolt not complete, or this not completely fixed. Then it would be somehow connected, because due the shape of the screw, and that there is a hole inside these two plates, it would not be possible to do everything with these two parts. Somehow the degrees of freedom would be limited. So you were not able to translate this in let's say this direction and this direction. Let me mark it, baby, it's easier. Just need a pen. Isn't here a pattern? Okay, then let's do it another way. Okay, this is also guys, sorry, just 1 second. Okay, let's do it completely another way. I will take a snapshot here and then use paint. Sorry. Okay, so the screw of the bolt now is limiting how you can move. So this is not possible anymore. Because it's fixed, but you could still move it theoretically in this direction. If there is a small gap, for example, between the nut and this outer surface of this body. But this is also not possible if we assume that there is no gap. What is still possible, and that will firstly not change, is that we can rotate around this axis. And that's the reason, by the way, maybe you saw it, and why it's very important how much we are is putting preload on this nut. With preload, what we mean is here that you are still, let's say, fixing the nut more and more, even if it seems that there is no gap. And the reason for this is that such a connection between these parts is not working only because, or mainly because, let's say that the degree of freedom is limited by the bolt. The main working principle behind this friction in the end again, because when we are turning the nut more and more, at some point it cannot move because there's no gap. And then in the end, when we're turning the nut more, we are creating stress here between, for example, between these two plates. So here, but also here. And this force, this stress, is the reason then why it cannot move, because of the friction, it's not movable. And that can help us, for example, to make it on the first hand that rotation is not possible anymore, and the other, and what is more important, this will really increase, let's say, the strength of our connection. Because now, let's say, for example, if you would now put wrong color. If you would now, for example, put the force here, then without this preload, the force would just go through the bolt. But because we have preload now, this force F is not only transferred by the bolt, because now if the force would be transferred only through the bolt, we would have shear on the bolt or on the screw, and it would break. But now, because we have this preload and the friction, the force will be mainly, let's say, transmitted through the two bodies itself, and that makes the connection more stable, and also will reduce vibrations and other problems you can get. So this is are the two principles, let's say, of connect something. And that's why the reason when you, for example, think about changing the wheels of your car, you use this special special tool so that you have the exact, also let's say the perfect torque you need for have the best connection. Great. Are there any questions right now? Great, then we can start with the simulation setup. I know this was a little bit theoretically, but later on you will understand why this short lecture was important. Okay, then what we will do right now, it's the same, let's say, like last time. We'll upload the CAD model, we'll create the mesh, and then set up a structural simulation. And oh, sorry. And what we will investigate is the arm, in this case, of the drone. So this is our arm. We will just, yes, first at the first stage we will only investigate the arm. And when we simplify the problem, what we can say is happening that we have this lift force on the arm, which is created, yes, by the propeller and by the engine. This is what we investigated last time. And for a first shot, let's say we will just investigate if this lift can create structural problems on this drone arm. We will take only the drone arm and say it's fixed here and here. For sure, it's not only fixed, that it's a very, very, let's say, big simplification. And later on, in the homework, for example, we will remove the simplification and really make a more detailed analysis. Because, for example, here we are not taking into account the effect of the bolts, the preloads that we have, and the rest of the assembly. And so the first step, we will make a simple static structural simulation of this part. Okay, and therefore, let's switch to the SimScale platform. I think everybody knows how to log in right now, but maybe I show it again. So just go on platform.simscale.com, and then here you enter the email address or the username you have on SimScale. Then you enter your password, and you will be directed to the platform. And here you can right now set up the simulation in 3D. For sure, also prepared a project, but let's start again from scratch. So the first thing we have to do is to create a new project. Let's call it drone arm. Now the project is just created, and it's added to the project list on the left side. And now we will switch to the mesh creator, and first of all upload our CAD model. Again, you have to give it a name, otherwise we'll take the name of the CAD file, specify which file format you want to upload, and yes, step in from my experience is there the best choice, and take this CAD file which I have isolated from the assembly, which you can also download on our website. But for the homework, we will for sure provide you again with the project including the ready geometry. And click on upload. That takes maybe some seconds or minutes. It depends on your internet connection, because this is one of the few steps where we're really sending files to the platform or back. We're uploading just a CAD model, and now you can see here is our CAD model. First of all, or the first things you should check every time you're using a geometry, especially your own ones, is first of all if the scale is the right one. So here we can see the bounding box diagonal length, which is measured from the, let's say, two opposite points with the biggest distance, in this case here and here somewhere, and it's about 10 centimeters. So this is, I think, the right scale, because it's very important that when you export geometry, which you want to use at SimScale from a CAD system, that you choose meter as a standard unit. And we can see there is one solid in this geometry, which also makes sense, because if there wouldn't be a solid, then you cannot use the model for a simulation because it has a leak. Yes, next step is to create the mesh. We talked a little bit about last time for CFD simulation, for FEA simulation. So FEA is the let's say, scientific term with finite element analysis. This is another approach which is used mainly for structural simulations. And as I mentioned, it's quite similar. You need a mesh because your CAD geometry, you know, is somehow has a limited number of points, and since the computer is limited by memory, for example, you have to define where exactly you want to calculate the physical quantities. And for sure, more points, so a finer mesh. Those points are later on, let's say, how connected to mesh. As more points you have, or nodes, it's the right term. as more accurate is your result, but it will also increase in the time for calculation. And so in the best case, you're looking for the simulation result where you have as many sites as necessary and as less as possible. And we will now create a mesh based on the geometry uploaded. So we will can also give a name for the mesh and specify here the base, so the CAD model. So we will in the end mesh this geometry. That's the term simulation engineers are using. Yes, and now this mesh operation or mesh project was created. It's part of this sub-part of this bigger project. And first of all, what we will do now is add the mesh operation. And here again, there are a lot of different meshing tools or meshing algorithms we can use. Last time we used SnappyXMesh, which is can only use for CFD. And today we will we will use a TED mesh algorithm. So the geometry is not divided in hex headers but in tetraheders. And we will use not the automatic one, but the tetralization with refinement, so where we can manually define the coarseness of the mesh. Yes, and it's here a little bit similar, like working with SnappyXMesh. So you first of all have to define a kind of, let's say, base mesh size. And then this base mesh size is used first of all for everywhere, and then you can specify regions where the mesh should be even finer. But here again, there can be none of the elements will be bigger than the maximum mesh edge size you define here. And if you want to make it finer, that's possible. And we are entering here a range because this is a smart mesher, so it will use this range in the best way. For example, because when you have you cannot, if you have a fast change of mesh size, it can also influence the quality of your simulation result. And yes, so we have to specify these two numbers here. And we will start with a mesh size of, this is 6 millimeter as the maximum mesh size, going down to 1 millimeter. Then here you can define, choose if you want to have first or second order mesh. And this is really quite important, and I will tell you why. I don't want to go too deep, but in the end, what we are doing with the meshing is that we want to approximate the solution. So our solution would be the field, the result field where we have the stress and the forces for everywhere in the model. And there are two approaches. So if you use first order, you can imagine it like this. When you have a first order mesh, and let's say this is our mesh now, so we have these are these two nodes. If you have a first order mesh, no, I think better. Okay, and let's say this is the first order mesh, and both meshes will optically look the same. But with first order, you would use a kind of a function between these 2 points to interpolate the values, which is linear. We take another color. And with second order, we're using a kind of spline interpolation between the points. So a second order mesh, and that's in the end the lesson which I want to give you right now, is more accurate with the same number of points. But creating a second order mesh for the algorithm, as well as solving it later on, is quite more complex. So second order is better in general, but if you're able to do it also with first order, you should really think about it, because it can prevent a lot of problems. And I would suggest you as a beginner just to use first order meshes. Great. Then let's start really with the mesh design. So I forgot to save, so it's lost. It's very important. Press the save button every time you change something. So let's call the operation 1 as a title for this mesh operation. We can change it, but we won't. So our base mesh size is 1 millimeter, and it can be up to 600 micrometers. We will use a first order mesh for the cause and use 2 processors, because it will be a small mesh. Now press save, and then we can add the mesh refinement. And so now we will manually tell the mesher where to make the mesh finer. And the reason is that everywhere where we expect high stresses, we need more elements to calculate the stress more accurate. So there can be kind of rule, let's say, where you prevent high stresses, high changes, makes mesh finer. And where we will, because you have to imagine later on our mesh will be like, we will fix it here and pull from here with 3 newtons. So it will bend somehow here, and therefore we should make this surface finer with a finer mesh. And this is something from experience. When you here also, I think there will be stress, because these are parts where it can easily deform. And last but not least, we will also here make it finer. So then here, by the way, what I was doing right now is just using graphical selection, because refinement is like this. You give it a name, you define how it should be refined, and then you assign it to something. We will assign it in this case to faces. So I've just selected them with the left mouse button. You can choose what you want to select graphically: volumes, faces, edges, or nodes, and then just click on Add Selection from Viewer. Then it's here, add it to the list. And here, because we want to mesh finer here, we will make 60 from 30 to 1 micrometer. No, sorry, 300 to 100 micrometer. Sorry. And make it here moderate, so a little bit more fine, the refinement parameter. So just let's give it a name, something like high stress refinement. Save. Right, now everything is ready, and we can just start the meshing operation, clicking on Start. And since this mesh will be quite smaller than the meshes for the last time, in general FEA meshes are smaller than CFD meshes, because it's another different mathematic approach. This is faster. And maybe sometimes it takes a little bit longer when the platform is full of jobs. It can take up to let's say up to 5 minutes till your job is started, especially when so many of you are doing simulation. Okay, so what we just learned in the last minutes. I showed you how to upload a CAD model on SimScale, and also how to check if the model was exported right. Then we talked in general about TED mesh refinement, about the difference between first and second order meshes. So which is what I sketched for you. And yes, in the end you had a brief overview about manual meshing, so how to create a mesh based on a base mesh size, and how to create local refinements. And you cannot only apply refinement to a face, you can also apply it to a whole body, so to a volume or to an edge. So there are nearly unlimited possibilities. And what we're not talking about, but what is also important, is CAD cleaning and preparation. It's it's in the end the same like for CFD. So you should try to simplify the problem as much as possible, and that starts with your CAD model, because there are sometimes small details which have no influence on the result later on. But for example, if you would have a very small feature, let's say, which is really, I don't know, half a millimeter thick, for example, to measure it is a big problem, but it will not change your results. So you should not really use it. You should more simplify it before. And also for FEA simulations, the mesh quality is quite important. I don't want to go too much in detail, but you can imagine what we call mesh qualities and the structure of the mesh. And just to give you a maybe not scientific, completely correct, but very vivid image or comparison, you need to calculate, for example, the stress here at the point, let's say in the middle of the arm. You also somehow need the stress or the force here. And quality means that there are some rules, let's say, which the measure is taking automatically in count, or try to take automatically in count, how the points should be located to each other. And if the geometry is quite complex, then it will not work, because in the best case, an element should look, element should really look like this. And then you have here the nodes and one element in 2D now, but in reality is 3D. And a bad mesh, for example, when you have a sharp edge or something like a small feature, then it can happen that the element gets skewed. And then it's not so easy for the solver later on, for the algorithm to calculate the simulation result, and that will also have an impact. So the result here will be not very good, and will also have an impact on the neighbor cells. Okay, so maybe just to make it vivid, this is good. And this is bad. Great. I think the mesh should be ready in the next minutes. So you can see the meshing job is currently running on the platform. And it maybe take some more minutes, but as I told you, I'm prepared. So there is a complete ready run of the simulation. I will just now copy the project, delete the simulation, and then we can together set up the simulation. Okay, great. Then, so when the mesh job is done, you can see the mesh. And here you can also really see what I mean with refinement. So we have this base mesh size here of 1 millimeter here. And everywhere where we applied this mesh refinement, for example on the face here, the element size was reduced up to 1/10 of a millimeter, and then this algorithm is automatically varying at the border between two let's say fineness levels, automatically adapting the mesh size, so it's smooth. It's very smooth from the coarse to the fine cells. And the mesh was also refined, for example, here. And maybe one thing I didn't demonstrate the last time, but you can also check, because it's a volume mesh, so we're not only meshing the boundaries, but also the volume of the part. You can also check the inner part of the mesh using the mesh clip filter. So this is a plane, and through this plane, the mesh will be clipped. So if we do it here, the arrow is showing which direction will be clipped. You would see the whole mesh, or if you change the arrow, nothing. So we will manually move this plane using this menu here. And you can see the geometry is, because it's a coordinate system here, is a little bit rotated into the coordinate system. So we will just put a second normal in, and then it is right. And then, for example, we could now clip the mesh here. Or if we want to have a clip like that, so that we can make a, and now we can clip in this direction. And now we just change the reference point. So and here we will put it, let's say, to -1 centimeter in that direction, so in this direction, and also in X direction. A little bit more, it's too much. And still too much. Okay, or let's put it completely. Sorry, wrong one. Okay, now we can just click on apply. And this sometimes takes maybe a minute because now the mesh has to be proceeded. And this is like everything which is computing intensive, not done on your local computer, but in the cloud. So you are independent from your local computer, from the performance of your local computer. And then we can even take a look inside of the mesh, like here. Double click with the left mouse can help you to change the center of rotation, and now we can take a look into the inside of the mesh. Okay, great, let's start to set up the simulation. Now, it's similar to the aerodynamic simulation. First of all, we have to create a new simulation. You can also change the name. And then we have to change which kind of simulation you want to perform. For solid mechanics, first of all, you choose, let's say, the kind of simulation and then some details. For solid mechanics, there are different options. We will do a static analysis, so that means we will just look at a steady physical phenomenon. So time is not really, there's a pseudo time simulation. Time is a pseudo time, so it's not really a transient simulation. And we will use advanced since we want also to take contacts later on, so interaction between multiple parts. And in this case, especially because we also want to know or investigate nonlinear physical phenomena. So nonlinear, as the name say, means that the stresses are not behaving linear from then, and that can create something like plastic deformation is not linear. Okay, then first of all we have to select the mesh we want to use. In our case, we just have one mesh, which is then immediately shown here. And since we have only one part, we don't have to care about for contacts. So the standard contacts are defining how the different parts of the model are interacting, and physical contacts are also considering also interaction between these contacts. So this is not important since we just have one single part and not an assembly. So the next important thing for us is to define the material, or to assign the material model to the part. So to say to the solver, or to say to SimScale, which material is this part made of. And basically, you can create your own materials. So you go on this Add Material button, and then you can specify a material completely yourself if you want. But you can also, because we have a material library, use the library for this. So, for example, for steel and other metal materials, we have most of them in the library, but you can also define everything yourself using the fields we're providing. Okay, then let's start. I told about the material library. You can find it here, but the arm will be 3D printed, and we have only no 3D printing material here. Therefore, I did some research online, and the material used in the most 3D printers is ABS if it's an extruded printer, and then we can rename the material. The material behavior is linear elastic. It's isotropic. And then we have to enter the Young's module, which is also in some other books called the E module, so it's the elastic module of the material. And we have to enter the Poisson's ratio, which depends for three-dimensional material how the relation is between the elasticity in different directions. But these are values you can just find out in the internet. We have no creep, and we have to enter finally the density of ABS. I took all those values from the website of a 3D printing company. And then finally we have to assign it to the part. And if you have assembly, you can assign different materials to different parts. But since we have only one part, we will select it again graphically, but you could also do it here in the list. And now we have assigned the material. Initial conditions, we don't have to touch them. We have no initial conditions, so we will anchor it blank. And what we do now is the boundary conditions. And again, like CFD, boundary conditions are describing how my model is interacting with the environment. There are two types of boundary conditions for the static FEA analyzers. First are constraints. So they are somehow describing how the degrees of freedom, the kinematical degrees of freedom of the model is limited. And loads, which are more describing, or which are used to define really, for example, forces, torque, so how external loads on the model. And in our case, if we take a look again back on the sketch, we want to fix it with the surfaces, the arm. If it's not fixed, nothing will happen, because then the force will just move the part and the simulation will crash, and we will apply external force lift. And so let's say with a constraint, which is with fixation, let's call it fix. And then we just select here, pick faces. We will select these two surfaces. Type is fixed value. So fixed value means that we are here really not defining the gradient. Something is really the value which should be later on the solution field. So we are now just defining a value which will not be changed by the simulation later on. In this case, we can't want to have it fixed. We can decide the displacement, and we still there will be no displacement. So these two faces are fixed; they cannot move. And here, change to faces, and then assign it to this both two faces with this Add Selection from View button. And yes, the other option will be, by the way, unconstrained. That means that it can move, but everything is fixed now. And now we have to add the load. Last time we calculated the lift force created by a propeller. So we change type force. Please note that really it's a load boundary condition or the constraint boundary condition. Then we will again select the face we want to apply it, and let's say a simplification on this whole face. So the force will be calculated into a kind of pressure and applied on the. So if the whole face, the force on the surface is the value we add here, and yes, it's in y direction, and I would suggest to use 3 newtons, which is yes a realistic force, since we know from our last simulation projects about aerodynamics. And just click on, let's give it a name again, lift, save, and now we have also lift. And now the simulation is nearly done. We don't have to touch numerics still because the standard values are quite fine for us. And now simulation control. Please use auto, because in contrast to CFD simulation, FEA simulation is not iteratively. So it's not like we start with the initial start result, and with every iteration it becomes more and more accurate. There is in one step everything is calculated, and therefore if you do manual now, in standard values is 0.01 second simulation interval, and it's still static. This is just pseudo time, simulation time, and 0.001 time length. It would do 10 simulation steps, but it's not necessary. We just need one simulation step. So with simulation interval 1 second and time step length 1. If we would put it both to 10, it would be the same result, by the way. And we will use, in this case, 4 computing nodes. And the simulation will not least one or take 1 hour, more than 1 hour, so we can, its maximum runtime is again the same option like for safety simulation, not touch it. Just on save. And then the last thing we have to do for FEA simulation, there are so many more derivated quantities than for CFD. There's, for example, a lot of different ways to calculate stress. And by default, these 3 fields are calculated, but you can't add additional result fields you need. So, for example, here we will add von Mises stress. It's a convention for how to define, let's say, stress. It makes it easy to compare stuff. Let's just call it von Mises, and then this field will also be calculated. Yes, and finally, we have to create a new simulation run. Click on Start, and the simulation will be now calculated, and we will be informed when it's done. Okay, so now let's do a small wrap-up again, what we learned about simulation setup. So we used the mesh we created before, took a look inside it, then we switched to the simulation designer tab and generated the simulation really. And this included, first of all, to select the mesh, but also define the material. So I showed you how to use the library for steel, for example, which is in the library, also how to use your own personal material based on material characteristics. Then we defined the boundary condition and both types. We fixed it using constraint boundary condition and applied the first using a load boundary condition. Then we added additional solution field because we also wanted to investigate or to have the von Mises stress in the solution, and then we start the simulation. What would be advanced at this point is first of all contacts. What it exactly means will become more clear when we talk about the homework, but just some words here. What we really now simplified the problem very much, because we say that this arm is fixed, and that's not true. It's not fixed like that it cannot move or cannot bend or something like that. This faces. In reality, it's an assembly where we have a screw connection with a screw and a nut, and there we have preload, and we also have an interaction between the parts. And if you have an assembly, so more than one part which are interacting, you need to define contacts, which are describing how the parts are connected on a kinematic and also from a physical perspective. This is something you will do in homework level 2, but we will again provide a very, very detailed and good tutorial for that. And we also didn't talk about numerical solver setup, and this is solver settings. This is not really important. You don't have to modify it even in the homework level 2. There's also some advanced solver control, which we will also use a little bit for level 2, but again, this will be explained. Great, then let's see. Unbelievable. In the meantime, our simulation was finished, and you don't have to wonder, but the convergence plots are looking different here. It's not a kind of plot, it's just points. And here you can see the largest residuum, and we just made one calculation step, and it's 2.5 e minus 10. So its convergence problems are not comparable to CFD. And this is a different chart, shows the number of iterations and the step count. Okay, so simulation is done. We can now switch to post-processor. And by the way, post-processing for FEA is quite more easy, and even with the beta version of the post-processor. And we go to our run, and first of all, we will take a look at the solution field. So, at the simulation result in 3D. And this takes maybe some seconds till it's load. I see there is a question, or two questions. First of all, Muhammad said that his screen, he cannot see the screen. Does someone else have a problem with the screen? So if you have a problem, raise your hand. If everything is fine, don't raise your hand. Seems that problem is solved for everybody. Yes, sometimes, it's a bit longer. And then Bulat asked if we could create a 2D mesh to capture true stressness on the surface of the 3D mesh. Yes, we can create later on clips and also slices to take a look to the inside of the part. Does it answer your question, Bulat? Okay, great. In the meantime, our result is loaded here. And now, first of all, what we will do is we have to jump to the time step. And we have only one time step, so press this last frame button, and then the result is really loaded. And now we can, first of all, you have this tree here. And the tree starts with the whole mesh. So we are seeing now the whole mesh here. And when you select this tree, you can here change the representation type. So if the surface, if you want also to, for example, to show the mesh, or only the outlines. But we will take a look at the surface. And you can change how it's visualized. So when you on select field default, it will be just gray, so solid color. But for example, we can take now a look on the stress of the whole body. And then we can also, where is the color bar? We can also here activate the color bar, and then we can see the stress here. And yes, as we expected, there is a high stress here. And again, our expectations, the stress here is not really high. The reason, in reality, the stress is here very high. The reason is that we fixed it here, and because this face cannot move in any direction, there is no bending. And we have also some more stress here on the inside. Yes. And this is really the leverage effect, that you have the lift here and this long leverage, this long arm. And what you also maybe not want to know now is what's about, let's say, the deformation. And for this, we will add a filter. So this filter is preceding the data. It's called Wrapup vector. And one of our result fields is behind stress displacement. And this will now visualize the displacement. We can also define a scale factor if the displacement is very small. And yes, now you can see, like here, for example, and let's change the color. So make this one to solid, and this red by color, let's color it by stress. And then you can really see the deformation here of the arm. So what is the colored part is how it would look from the view of displacement when you put this load on it. And you can really see, yes, the deformation. And what we can also do, for example, is make a slice. Save it first. And then let's say take a look now into the arm. And here again, for example, we can take a look at the stress. And here you see the highest stress we have is 1.8 E6 Newton per millimeter square. I think it's a standard unit of strength. And then you can also check the maximum stress, which is or maximum elastic stress of the material. If it's higher than this value, then you know it will break there or deformate plastically. Yes, and yes, that was our simulation. And if we want, we can do some more stuff now. For example, we can visualize other stuff like the nonlinear stress, the Cauchy stress, or every other field that we want to see. Yes, well, okay, so that was the post-processing. And we talked just shortly about how to visualize deformations, surface result plots, and slices. And what will be advanced is really if you want to create plots, if you have, for example, several simulations, or if you want to derive additional physical quantities which you cannot calculate while the simulation. Okay, well, yes, we are done with the simulation setup. And now let's talk about the homework assignment. Or are there any questions you would like to discuss right now? Just 1 second. I have to open the question menu again. Okay, then let's do the questions later on. And first of all, talk about the homework. Yes, today you will have again 2 homework lessons. When you have, we'll publish them tomorrow in the morning, and it's the first level is about in the end redoing the simulation I showed you, but not only for one force, for several forces. So we will have to measure it once and then create 4 simulations with a given range of lift force, and then you can somehow get an idea how this kind of simulation is, for example, used to optimize a product. And when this is done, so here you're doing 1 meshing job and 4 simulations, and all the 4 simulations, you don't have to create it again from scratch. You will just set up 1 simulation, then create the simulation, and then you can start the simulation, change the force, and create a new simulation. And level 2, we will exactly work on some of the simplification which I talked about. We will simulate the full assembly of the drone. So we will not fix the arm of the drone. We will put it into assembly with screws and nuts and simulate the effect of preload. So there you have to create a mesh and set up the simulation. But here we will do 2 things. First of all, you will see and understand the effect of preload and how to simulate assembly. And then you will do what we call it mesh study. So I talked that the fineness of the mesh is important for the quality. And what you will do is to create 3 different mesh, different refinements. And then you will run the same simulation and just check how the simulation result improves with final mesh. But again, for both levels, you will get a very detailed step-by-step instruction, and you will get all the support you need in the forum. Great, so we will put all the stuff again into the forum with the description what you have to do, with tutorial, somewhere you can ask questions. We will also provide you with the recording. Everything will be available tomorrow in the morning on simscale.com/drones. Okay, now let's talk about our questions. Please put all your questions into the question field. I will start with the first question of Hashada. And the question is if it's possible to check the mesh quality, like aspect ratio, like in other CFD or FEA tools. And yes, that's for sure possible. Therefore, let's go to the platform. And when we open the mesh in the post-processor, then we can check there the mesh quality. Let me just wait until it's loaded, and then we will check it together. sometimes what helps is just reload SimScale. Go to post-processor and open the mesh. Okay. Till it's loaded, let's just answer me another question. Pravin asked if SimScale can be used for composites parts, and actually right now it's depends what kinds of composite. When you're really talking about a high complex carbon fiber composite material, it's not possible, but we are developing this feature and it will be available in the near future. It's just a question of material model, because right now we're not supporting this shell elements, but it's in the pipeline, will be here, or will be available in the next month. Okay, then Christopher asked, Christopher, same question, sorry. Pravin said that he missed the first session due to the time zone difference. And he would still like to be part of the first session. As I mentioned, this recording of the first part is available on the website. You can access it. For example, then here is the video. But then you have to be fast, because we will only accept homework submissions till tomorrow morning at 9. Okay, are there some more questions? Great. Then, here's a question. What is the difference between linear and non-linear? Yes. Okay, maybe, I know maybe it's new for some of you. The difference between linear and non-linear material behavior is, as the word says, if, for example, the relationship, let's make me a short sketch. It's, in the end, just give you an example. If we have two axes here, and one would be stress, in one axis would be deformation. So, and let's assume it's just a cylinder which is fixed here, and we're pulling here. Then linear would mean that it's proportional, and non-linear would mean, for example, that's non-proportional, non-linear anymore. So that's the difference basically, but it's for sure scientific point of view more complex. Okay, great. So thank you very much to everyone for attending here. We're really looking forward to your homework submissions, to your questions, to the discussions, and I would really like to encourage you, motivate you, to do your own stuff. If you have your own idea, own modification, you would just do it, and you would get all the help in the forum. Okay, yes, guys, thank you again. It was a nice session, and yes, hope to see you next week. Bye.